In the very heart of modern science, among progressive laboratories and brilliant minds, lies one of the most enigmatic and philosophical topics, the connection between consciousness and matter through the lens of quantum physics. Let's begin our story by noting that the idea that consciousness can influence matter is not new. It emerged alongside the first discoveries in quantum mechanics at the beginning of the 20th century, when scientists encountered phenomena that defied intuition and classical logic. One of the key scientists who contributed to the development of this theory was Roger Penrose, a Nobel Prize laureate in physics in 2020. He proposed the hypothesis that consciousness is linked to quantum effects in the brain. In his books, such as Shadows of the Mind and The Emperor's New Mind, he put forward the idea that consciousness is not merely a product of neural activity, but manifests through quantum processes occurring in microtubules within our brain cells. This idea is supported not only by philosophers and science fiction writers, but also by a range of research. For example, the theory of orchestrated objective reduction is based on the assumption that it is precisely quantum states entangled in microtubules that are responsible for the formation of consciousness. The Orch OR theory, or orchestrated objective reduction, is among the most captivating hypotheses about the nature of consciousness, linking quantum physics and neurobiology. To understand its essence, let us imagine that, in our brain, something is happening that goes much deeper than the usual neural signals. At the foundation of this theory is the concept that within neurons, or more accurately, in special structures called microtubules, quantum processes are occurring. Microtubules are hollow cylinders composed of tubulin proteins, and they are generally thought to merely support the cell's shape. But according to scientists, they can act as a kind of biological quantum computer. What are quantum states? In classical physics, things exist in one state or another, like a switch. In quantum physics, it's different. A particle can occupy several states simultaneously and choose one only when measured. This effect is called superposition. In microtubules, particles in tubulin molecules can be in quantum superpositions, that is, in several states at once, enabling the execution of immensely complex, parallel computations. But what does it mean for quantum states to be entangled? Entanglement is a super effect in which two or more particles become so tightly linked that the state of one instantly depends on the state of another, regardless of the distance between them. It is proposed that in microtubules, many such entangled quantum systems form a complex network where every quantum computation affects another. This helps explain why human consciousness is so complex. It could function thanks to these entangled states, forming the illusion of a conscious self. The general mechanism is the so-called objective reduction, collapse of quantum states. Roger Penrose, one of the creators of the theory, believed that quantum states collapse not randomly, but according to an internal physical threshold. He named this process objective reduction, where quantum systems decide for themselves which state to realize, and this happens independently of any observer. In the case of microtubules, this collapse may serve as a moment of consciousness, since every collapse creates the sensation of an event, the sensation of I. So, what happens in the brain? According to the theory, microtubules in neurons act as a kind of quantum registers, where entangled quantum states and superpositions control processes associated with consciousness and thought. Each decision or choice is a moment of quantum state collapse. Their sequence and interaction create the feeling of I, which we perceive as a conscious experience. Why is this important? Because classical neurobiology cannot explain how random electrical signals and chemical reactions give rise to subjective experience. The Orch OR theory suggests that it's at the quantum level where those very processes occur that form the sensation of I, free will, and creativity. And while the Orch OR theory is still controversial, it opens incredible horizons. For its authors, the key to understanding how physical processes give rise to consciousness capable of creating reality is hidden in entangled quantum states. This raises the question, is consciousness truly something beyond material reality? Or, on the contrary, does matter itself create it only on a quantum level? Historically, even in the 1970s, physicists and mystics began searching for parallels between quantum physics and Eastern mysticism. Fritjof Capra, author of The Tao of Physics, explored ideas of unity and wholeness of reality based on quantum principles. His ideas were taken as a philosophical interpretation of quantum entanglement and superposition, which claim that particles, even at great distances, remain connected. Especially notable in this context is the work of Victor Stenger, who asserted that consciousness is not just a passive observer, but an active participant in shaping reality. He considered observation an act that creates matter, which closely matches double-slit experiments, where the act of observation changes the behavior of particles. This phenomenon prompts us to consider, can consciousness really create matter? Victor Stenger is a bright figure in science, whose voice sounded powerfully and convincingly in discussions on the nature of consciousness and quantum physics. Born in 1935, he was not just a physicist, but also a philosopher of science and author committed to clarifying complex topics for the general public. The name Stenger became synonymous with a critical and thoughtful approach to popular, yet often controversial ideas associated with quantum mysticism and consciousness. Stenger himself noted that many interpretations of quantum physics regarding consciousness are prone to excessive speculation. He opposed turning the strictest science into esoterica, which earned him respect from both the scientific community and thoughtful readers. His book, Quantum Mind, is an attempt to distinguish reality, scientific facts, and conjecture. Stenger's work is interesting because he recognizes the mysterious nature of consciousness, but emphasizes consciousness is not a magic formula that changes universal physics. He respects the quantum world, but is convinced that most mysteries should be solved through further research into the brain and neuroscience, and not by transferring quantum effects to consciousness without sufficient evidence. His well-known quote, "It's often said that the observer in quantum physics creates matter, but an observer in experiments can be any detector, not necessarily consciousness." This is an important remark, highlighting the need to distinguish physical measurement from subjective experience. Stenger was also an active participant in debates about the scientist's responsibility for clarity and honesty when popularizing science. His works serve as an example of how one can be both a skeptic and seek new horizons. Among Stenger's scientific achievements are substantial contributions to astrophysics and fundamental quantum systems research. His legacy is a reminder of the need for balance between introducing new theories and testing them with experiments and logic. Thanks to scientists like Victor Stenger, the scientific community maintains a critical perspective while keeping the inspiration and desire to understand the secrets of consciousness and matter. Modern experiments confirm that observation is a key factor in quantum processes. Research shows that under certain conditions, microtubules in the brain can display quantum coherence, allowing, according to the theory of Penrose and Hameroff, an explanation for subjective experience and the complexity of human thought. This idea sparks debate, but it does not rule out the possibility that consciousness truly affects matter through quantum effects. For instance, scientists have observed the behavior of tubulins, the building blocks of microtubules, at low temperatures and under specific conditions, where energy quanta stop dissipating quickly. This discovery became a kind of bridge between biology and quantum physics, offering hope of understanding how the brain interacts with quantum processes. Scientists then modeled how this coherence could affect neurons, triggering electronic signals that, in turn, influence brain activity. This explains why human thinking is so complex and flexible. It's based not only on classical chemical processes, but also on subtle quantum interactions within microtubules. Modern science keeps improving methods for observing quantum effects in living systems. Experts use ultra-sensitive magnetic and optical sensors, as well as quantum computation, to observe and understand molecular processes in the brain. While many questions remain unanswered, advances in understanding microtubule coherence are a vital step toward explaining consciousness from the standpoint of quantum biology. The core idea is that microtubules can work as quantum relays, switching and coordinating signals on the quantum level, thus producing conscious experience, high intelligence, and creative thinking, the very things that seem impossible to explain from the viewpoint of classical brain physiology. So, we have come to what may be called a fundamental mystery. Perhaps consciousness is something more than just a function of the brain, a whole universe of possibilities realized in the moment of observation. As Max Planck said, consciousness is fundamental, matter is merely its manifestation. Understanding this mystery remains an open quest, but each new study brings us closer to solving what it is in the world that creates our reality. Quantum physics experiments, like strange mirrors, reflect the paradoxes of nature itself. The 20th century gave us the double-slit experiment, an experiment that still fascinates minds and calls the usual worldview into question. Picture this: electrons or photons directed at a screen with two slits. When no one is watching, particles behave like waves, producing an intricate interference pattern on the screen. Yet even a hypothetical observer changes everything. Electrons carve their path as particles. The impact of observation has been tested thousands of times, and the result always depends on the presence of a conscious observer. This is the observer effect, a chief quantum anachronism requiring a fresh view of consciousness's role in the structure of reality. You might ask, does this mean that if the observer is a simple sensor without consciousness, particles act like waves, and only when a human watches do they behave as particles? It's important to note that the observer effect in quantum mechanics often causes misunderstandings. One of the most popular interpretations is that human consciousness is necessary for particles to choose their behavior. However, reality is subtler. It turns out particles behave as particles, not as waves, when there is interaction with a measurement system, whether it's consciousness, a camera, or a detector. Consciousness is not directly required to change the behavior of a particle. Mechanical interaction suffices. So, it is not human consciousness that alters a particle's behavior, but any act of physical measurement, interaction with the environment through instruments, that leads to the collapse of the wave function. This is what is called the observer effect. Measurement changes the state of the system, not just looking with eyes. This is a key distinction from popular mystical interpretations in quantum physics. This does not mean that consciousness is unimportant. It has its place in interpretation and philosophy, but experimentally and theoretically, the observer effect is an effect of interaction, not necessarily of conscious perception. Thus, particles respond not to human consciousness, but to the very fact of physical measurement. And it is this that changes their behavior from wave-like to particle-like. This viewpoint is supported by most quantum physicists and is central in modern science. In the 1920s, 1930s, the question of the observer's role seriously divided prominent scientists. Wolfgang Pauli, one of quantum mechanics' founding fathers, maintained that the observer's consciousness literally influences the course of the experiment. In this camp is Eugene Wigner, Nobel Prize winner in physics in 1963. Consciousness seems necessary to complete the process of quantum measurement. The opposite camp, led by Einstein, Planck, Dirac, insisted on the objectivity of physical reality. But disputes have not died down. The observer, like a genie in a bottle, never disappears. In the 1980s, theories grew more complex. The Einstein-Podolsky-Rosen paradox and Bell's theorem appeared. They assert that particles, once in quantum entanglement, entangled like twins, stay connected irrespective of distance. Change one. The other responds instantly, as though they sense each other beyond space and time. A paradoxical world where consciousness may be the thread uniting all that exists. Recently, scientists have begun to study whether the brain has devices that can preserve quantum coherence. As we mentioned at the outset, astrophysicist Stuart Hameroff and mathematician Roger Penrose proposed the theory of microtubules, strange protein structures within neurons capable of sustaining quantum organization even in the warm conditions of the living brain. The quantum neuronal avalanche, where random quantum events trigger neural networks activation, is one more facet of this mystery. At the same time, philosopher David Chalmers calls the problem of consciousness the hard problem, as it is unclear how subjective experience, the sense of self, arises from neural activity. The quantum consciousness model remains merely a bridge over this gap. What would any researcher wish for? Inspiration. Perhaps it is inspiration itself that is the phantom quantum mechanics within human experience, like launching an incredible experiment inside our own lives. And yet, the peculiarity of modern science is that its discoveries give birth not only to new technical possibilities, but also to new myths. Quantum physics and the very idea of consciousness as a creative force have become the ground for speculation, mysticism, and even pop culture. If you're intrigued by quantum world mysteries and the enigmas of consciousness, don't forget to subscribe to our channel. Like if this material piqued your curiosity, and share your thoughts in the comments. People often cite alleged words. Consciousness is primary, matter is secondary. But from the first experiment to the last, this question remains open. Murray Gell-Mann, Nobel laureate, on the contrary, scoffed at quantum mysticism, insisting that any explanation of reality must stay within strict science, not turn into a fairy tale. But where is the boundary? Science makes us test every hypothesis. Physicists defending the esoteric reputation of quantum ideas bring forward experiments, for example, those with delayed quantum erasure, when the observer learns the information after the experiment, and, as some believe, chooses reality retrospectively. Let's try to explain, as simply and clearly as possible, how the delayed quantum erasure experiment works, where witch path information about a photon can be erased after the photon has gone through the slits and been registered by a detector. Picture a laser emitting individual photons, tiny packets of light. These photons travel and pass through a plate with two slits, like in the classical Young's experiment. Here, the photon may take either slit and, under normal circumstances, behaves like a wave, creating an interference pattern on the screen. Now, an unusual detail is added. After the slits, the photon enters a special crystal that splits one photon into two entangled photons. They are linked. What happens to one instantly affects the other, even at a distance. One photon in the pair, the signal photon, goes to detector D0, where it is captured, at a moment when its fate seems sealed, having already passed through the slits. The second photon, the marker, goes to another part of the setup. There, experimenters choose either to find out which slit the photon passed through, thus preserving path information, or to erase this information, making it impossible to say which path was taken. If path information is erased, meaning we don't know which slit the photon went through, then the interference pattern appears. The photon acts as a wave. If the information is preserved, the wave pattern disappears. The photon behaves as a particle, passing through only one slit. The most remarkable aspect is this. The decision to know or erase the path information is made after the signal photon has already been registered. It seems as though we are influencing an event that has already happened. Choosing later changes the past. In reality, this is not time travel or a mystical reverse effect. This is how the nature of quantum entanglement and superposition works. The combined system of two photons remains whole until both parts are measured. Only by considering the complete information, including the outcomes for both photons, can we determine when interference appears and when it does not. This experiment suggests, in the quantum world, there is no classical, definite history of events until we measure all associated parts of a system. Time here behaves differently than in everyday life. Thus, the delayed choice quantum eraser is a splendid example of how quantum physics transforms our understanding of reality, forcing us to reconsider concepts of time, causality, and observation. This experiment demonstrates that the decision to observe wave interference or particle behavior is made not when a photon passes through the slits, but later during the processing of path information. This doesn't mean that the past actually changes or information moves backward in time, but it points to a fundamentally different view of causes and effects in the quantum world. The experiment was first performed by Yoon Ho Kim and colleagues in 1999 and has since been repeated several times, confirming the amazing properties of entangled quantum systems. It is a key example of how quantum physics forces us to reconsider our everyday understanding of time, observation, and consciousness. Alain Aspect's experiment, confirming Bell's theorem, finally undermined faith in classical locality. He showed that objects can be physically separated, yet remain linked by invisible threads of information. In the early 1980s, Aspect and his team conducted an experiment that was a true demolition of the classical idea of locality, the notion that objects can only affect each other through direct interaction. The experiment used pairs of photons born simultaneously and linked by polarization, their electromagnetic wave states. These pairs, like twins, even when separated by space, keep an amazing connection called quantum entanglement. A photon sent in one direction seems to know what its entangled partner does even at a great distance. Aspect skillfully measured the polarization of each photon, changing the orientation of polarizers very rapidly and independently, sometimes under conditions where light couldn't transmit signals in time to maintain the link in the usual way. The results showed violations of so-called Bell's inequalities, strict mathematical boundaries that should hold if we use local realism. This meant that influence exists instantly without delays or signal transmission, contrary to the classical concept of locality. Thus, two physically separated photons remain bonded by invisible threads of information, affecting each other in sync. Aspect's experiments transformed the philosophical disputes of Einstein, Podolsky, and Rosen into realistic scientific proofs, confirming quantum entanglement as a real and fundamental phenomenon in nature. This work was later highlighted in foundational textbooks and even became a key basis for developing quantum technologies, from quantum computers to quantum cryptography. Metaphorically, Aspect's experiment is like two musicians on opposite sides of the planet playing so harmoniously, it's as if they hear each other instantly, breaking the traditional rules of space and time with no effort. This experiment stands among the great discoveries that open the door to understanding the astonishing and mysterious quantum world, where consciousness, matter, and information are tightly intertwined. The quantum consciousness theory is still not universally accepted. It remains marginal because on the macroscopic scale, at the size and temperature of the brain, maintaining purely quantum states is nearly impossible, as molecular activity and heat should destroy such organization. But recent observations indicate certain quantum events can trigger neurons, and the brain itself behaves like a giant amplifier, catching and inflating these random events to the scale of thoughts, feelings, and actions. Perhaps it is at the intersection of science and myth that the most piercing stories are born. Scientists, like explorers of new realms, make choices daily: what to call real, what to call possible. And for a person living between the dimensions of physics and their own self, it remains to watch reality closely and perhaps one day create matter with the power of their consciousness. What changes in our worldview when we perceive consciousness not as a random epiphenomenon, but as part of the universe's very structure? Storytelling is everywhere. In the nighttime lab, a student physicist suddenly detects an anomalous noise in the apparatus, coinciding with a burst of creative insight. "I'm sure something material arose from my amazement," he says. A similar story happened to Penrose himself. The idea of an impossible figure came to him not from logical reasoning, but as if from the space of possibilities where all scenarios were possible. The idea of an impossible figure is a geometric paradox, a drawing that looks whole and ordinary on a plane but cannot be constructed physically in 3 dimensions. The Penrose triangle is a figure made of 3 beams joined at right angles, but together they create a closed shape that defies the laws of Euclidean geometry. Penrose said the idea emerged from the space of possibilities where all options exist simultaneously, and he saw the figure there as if it had its own mysterious life beyond conventional boundaries. This idea later inspired the Dutch artist M.C. Escher, who created the famous lithograph Waterfall, a kind of visual story where water climbs an endless staircase and then returns, producing an endless cycle, an illusion of the impossible. Penrose's story reminds us that, in science, creative imagination is as important as logical thinking. It lets us glimpse where the deepest secrets of consciousness and the world are hidden. His discoveries laid a foundation for concepts where physics meets philosophy, where the possible and impossible intertwine, and consciousness creates reality itself. New physics offers an unexpected metaphor. The universe is not a book written in ink, but a quantum novel where the pages themselves can emerge from the reader's attention. As the famous philosopher Martin Heidegger wrote, "Being is that which lets be." Perhaps consciousness is not just light in a window, but the very window frame of the world. Over time, the focus has shifted. Today's Nobel laureates do not dismiss unusual effects at the border of classical and quantum reality, but they urge colleagues to be careful about hasty conclusions. For example, the Polish-American physicist Wojciech Zurek offers the formula of decoherence, the chaos that turns the quantum world into familiar matter, cutting off the supernatural. But even he admits, we don't fully know how this transition takes place. Inspiring observations. Japanese scientist Masaru Emoto conducted controversial experiments with frozen water, trying to show that emotions change the structure of crystals. Trying to explain this in terms of strict quantum mechanics meets physicists' skepticism, but there's no doubt about one thing. A person can calibrate the universe with their attention, even if not literally creating matter from nothing. Diving into the remarkable world of quantum physics, together we discover new horizons of knowledge. Subscribe to the channel to stay updated on this journey. If you enjoyed this story, give it a like and leave your comment. Let's discuss and develop ideas together. We stand on the threshold of a new way of seeing the universe, not so much as a collection of isolated objects, but as a floating sea of possibilities, where every conscious action is a moment of creativity in a vast probabilistic network. Now, physicists see consciousness not as a magic wand for matter, but as a subtle antenna, picking up the noise of quantum fields. The world no longer seems a set of solid bricks, but turns into a pulsating fabric, where each of us is co-author and witness. From the biographies of great scientists, it is evident theory, inspiration, intuition, and even everyday observation can prompt a true quantum shift in our thinking. As Viktor Frankl, who survived the horrors of war and created a new philosophy, said, "Man is free to choose his attitude, and in this lies his power." Previously, the boundary between spirit and matter seemed impassable. The era of quantum physics has shattered old walls. We now know that even nothing can be embodied if we shine upon it the light of attention and thought.